All right, so we talked about the charging case. Let's go ahead and talk about the discharging case. Actually, really similar. Let me go ahead and just copy a lot of this stuff. A lot of it's going to be almost identical. Go ahead and take a copy of this and just paste it right here. Make it a little smaller so it fits. And so the only difference here is that instead of starting at 0, the capacitor is going to be charged initially, okay? So instead of this value here being VC final, that's going to now be my initial capacitor voltage, okay? And instead of this growth, let me get rid of that, and let me get rid of this, and then I can move this here. VC initial, so my pulse source is now pulsing from some voltage down to 0, okay? And my behavior here is that my capacitor voltage starts at some initial value and then decays exponentially down to 0 like this, okay? So it's basically the opposite case of what we had in the charging case. The capacitor is discharging down to 0 exponentially rather than charging up to some value exponentially, okay? And so similarly, we would go ahead and just have an initial condition given to us. It would be that VC at time t equals 0 is going to be equal to some VCI. It's not going to be equal to 0 in this case. But now we also know that our final voltage, right, VC final, has to be 0, right? It's the value that this source ends up at, which is 0. That's what my capacitor is going to discharge down to, is a value of 0 volts, okay? And so if I want to come back and assess the FIFE equation and see how this fits into the FIFE equation, I can write it out right here. VCI minus VCF e to the minus t over RC is equal to VC of t. And so what do I know? Well, I know that my VCI is going to stay the same, but my VCFs are both 0. That's my final value. So both of these go away. And what I'm left with is just VCI e to the minus t over RC is equal to VC of t for the discharging case. So this is my expression that I can use for the discharging case. And let's take a look. If I plug in t equals 0, right? Let me take my laser cutter. Then, sorry, laser cutter. My laser pointer. Sorry, I've been using the laser cutter a lot for my project I'm working on. My laser pointer, if I plug in t equals 0, then this term goes to 1, and I'm left with just VCI, which is exactly what I expect at time t equals 0. The voltage across my capacitor is VCI. Well, at some time later, t is large, this whole thing goes to 0, and my voltage is 0, of course. And then everything in between is the exponential behavior derived by intermediate time values, okay? So I've talked about charging, I've talked about discharging. Hopefully these two cases make sense. This is the bulk of what we're going to be learning in RC circuits. There's obviously the circuits are going to get slightly more complex. I'll move some resistors and capacitors around, but the gist of it is always the same. This expression, FIFE, is vital. Obviously, it is how we derive the charging and discharging expressions that we use to determine these voltages. It can also be used to determine the currents, of course, because we know that the capacitor current is just C times dVc dt. So if we take the derivative of either one of these, then we can determine the current that's flowing in these circuits as well. Okay, so I'm going to go ahead and stop this video here. And in the next video, I'm just going to give a little bit more insight about what's happening with e to the minus t over RC and what this RC means in the scheme of these equations. What does it tell us? Okay, so I'll stop the video right here.